All right, so today we're going to close out chapter 8. So we got a few more reactions of alkenes to learn about here. Okay, so the first one that we're going to talk about are halohydrins. This is the addition of Br, well, I guess it's going to be any halogen, X and OH, right? Where X is one of our common halogens here. Okay, so these are halohydrins. On one carbon is going to go the halogen, on the other one is going to go an alcohol group. So we're going to get a mixed functional group product here. Okay, so if we take a simple alkene, all right, we got some familiar looking reagents here. The bromine, we'll do bromine. And water. All right, again, to one carbon is going to go a halogen. And on the other carbon goes that alcohol group. Okay, so our substrate again, as always, are these alkenes. Our reagent is now a halogen. In this case, we're going to do an example with bromine and water. And our product here is this addition product where we get both a Br and an OH on our alkene. Okay? And we just want to note that I drew this particular product. This is a regioselective reaction where the OH goes on the more substituted carbon. All right, so I specifically put that OH group on that middle carbon because it was a secondary carbon. The OH is always going to go on the more substituted carbon. All right, so this reaction starts out a lot like our halogenation reactions. We get that cyclic intermediate. Okay, we have a bromide, but now we also have water in the mix. Okay, both the bromide ion and water are nucleophiles, but in this reaction here we got a bunch of water floating around. Let's just note that we prepare these reactions with an excess of water. So that's what's going to play the role of the nucleophile opening up that ring. We looked at these mechanisms before, and we were adding a bromine to either side. So we weren't really too picky about which carbon the nucleophile was attacking in our cyclic intermediate here. But now I'm specifically drawing water attacking that secondary carbon there instead of my primary carbon. All right, so let's just note H2O will attack the more substituted carbon. All right, and there's no carbocation intermediate. But instead we can understand this if we look at the transition state of this step here. Remember, your transition state is that point when these bonds are like half broken and half formed. Okay, so we got this bond here. I'm going to draw it as a dotted line for a half broken, half formed bond. Actually, let me just draw it on the other side. Okay, so this here we have our water, this is our half-formed bond. And this is our half-broken bond. Okay, and so it turns out that in this transition state here, that carbon is, it's losing a bond, it's gaining a new bond, it's going to be left with a partial positive charge, while our water and our bromine have this partial negative charge. Okay, and so again, the more stable transition state has that partial positive charge on the more substituted carbon. So similar argument we've seen a bunch here. Now we're talking about the transition state instead of the intermediate. It exists in a very sort of short, fleeting fashion here. All right, but nonetheless, we're going to get that OH on our more substituted carbon. Okay, so let's finish off this mechanism. Everybody take a second and draw me my product of this step here. Okay, so now I have broken that triangle open, so my bromine is on that first carbon. Okay, but on this carbon now I still have just a water's been added. All right, my bromide ion is still floating around. What's missing from this step here? The positive charge, right? So I have neutral, my net charge has been neutral all along, so I'm missing that partial positive charge on the water. Okay, and then so how am I going to finish this off? My bromide is going to help in this proton transfer to finalize this here. And so we see that we also get this product of HBr if we were writing a balanced chemical equation. But again, in organic chemistry, we get lazy and we only really care about what's happening to the organic molecule. So you'll see it sometimes written with plus HBr, and sometimes you'll see that omitted altogether because it's an inorganic product. All right, so let's just make some notes here about this reaction. Okay, This is a reaction where we know its mechanism. It goes through that same cyclic intermediate we've seen before in our halogenation reactions. All right, this reaction is regioselective. They call it Markovnikov, but I don't know I don't know. It's kind of hard to say because you got a bromine and an OH group. So let's just say OH on the more substituted carbon. All right, and what about the stereo selectivity of this reaction? Is it going to, right, so our addition reactions, we had two types, a syn or anti-addition. Okay, looking at our mechanism here, what do we think this one's going to be? Why anti? Because of that cyclic intermediate. Same thing we saw before, right? That triangle is going to form on one side of our double bond, so the only way that our incoming nucleophile can attack is from the opposite side. So this is an anti-addition. All right, so we can take this thing and do something cool with it here. Our product, our halohydrin. And that is to form an epoxide with it. Epoxides? Yeah. So epoxide, you may have heard of, they're commonly used ingredients in glues, very strong industrial strength glues. And they always have like these two chambers that you mix together and that kind of activates the glue. So the epoxide itself is this very odd structure. It's something that we don't really see too much. It's a triangle. Right? Not something that we think of as being super stable, with an oxygen. All right, so two carbons and an oxygen make an epoxide. Okay, and these are stable enough that you can isolate them, but as we talked about with our triangles, they don't like to be forced into those bond angles, so these compounds here are very reactive. They're good starting points in a synthesis. Okay, and in particular, they want to undergo these ring opening reactions. Not at all unlike what we saw for our cyclic intermediate that undergoes this ring opening reactions. Our epoxides want to do the same thing. Very unstable triangle formation. They're trying to pop open and increase their bond angles. Okay? And so if we treat our halohydrin product from the previous reaction with a strong base, we will get one of these epoxides. All right, so our reagent here that we would buy from the store is sodium hydroxide. whenever I see a metal in there, I just immediately ignore it and put a minus sign on there, right? Because our metal isn't actually playing a role, it's just a counter ion. So sodium hydroxide is really an ionic compound between a sodium ion and a hydroxide ion. That hydroxide ion we know is what? What do we know about hydroxide? What role does it play in a lot of chemical reactions? A base, right? It's a base. So that's what a hydroxide is doing 99.9% of the time for you. It is playing the role of a base and accepting a proton. And so that's exactly what happens here. Your hydroxide is going to deprotonate your alcohol. All right, and now you get, whoops, let me not forget this guy. You get our first ever intramolecular reaction here. Okay, you have this lone pair on my deprotonated oxygen that's going to play the role of a nucleophile. You have this carbon, right, in a polar bond with a good leaving group, going to play the role of the electrophile. All right, and so this pair of electrons comes down here and kicks off that bromine, leaving us with our epoxide. And again, just to be clear, these pair of electrons here, that was what was originally on my nucleophile.
So is dissociation not working for this because it's not actually being a solvent in this case?
Dissociation? Well, so the sodium ion and the hydroxide ion do dissociate from one another.
Okay.
But there's no, the hydroxide ion itself is a package deal, right? So that's not going to further break down in solution. Okay. It will play the role of a base and steal a proton, though. So our last two reactions that we're going to cover here fall under this category of a diol synthesis. What do we think a diol is? What's the prefix di going to mean? 2. And what's all? What do we use for that? Anybody? We haven't really explicitly talked about this functional group naming yet, but we've encountered it a ton in the lab. Alcohol, right? So this is going to be the formation of molecules with 2 alcohol groups. All right, so our first one is going to be using that epoxide that we formed. Okay, these things really want to react. All right, so if we put this into any acidic solution here, we're going to get this ring opening reaction. Where we got an alcohol group on both of those carbons. All right, we're not going to sort of explicitly go over the mechanism here. It's actually not too bad. I think that we can figure it out, but we got enough mechanisms in our life right now, so we'll leave it at that. All right. We do want to make note, though, about the regioselectivity of this reaction. All right, that epoxide, if it's going to form this triangle, this is the same argument that we had with our cyclic intermediates. It can't form a triangle where one bond's pointed up and one's bond's pointed down, right? So that epoxide is going to form on one side of this molecule, which is going to lead, oh, sorry, this isn't regiospecificity. We got no regioselectivity. They're both OH groups, my bad. The stereoselectivity. Okay. Again, that incoming nucleophile has to attack from the opposite side. So this is going to be an anti-addition of those two OH groups. All right, now we just talked a lot about reactions that went back to back to back, right? We did one reaction, we took the product of that reaction, we did something else with it. We took the product of that reaction, did something else with it. This would be our first, what we call a multi-step synthesis here. Reactions that we can chain to make a particular product. All right, so let's just take a note here. And let's use a ring so we can show our stereospecificity of this reaction here. All right, so step one was that halohydrin reaction. Everybody take a second and give me the product of that. All right, so step one was the addition of a halogen and a hydroxyl group, an OH group. Okay, we called this thing here a halohydrin. We treat that with sodium hydroxide, and we're going to get our epoxide. All right, but since we have a ring, we're going to be really good, and we're going to show that this epoxide has formed specifically on one side of this ring. So I'm going to use my wedged bonds here. To show that that oxygen is on one specific side of that ring, all right, that epoxide triangle. All right, so then when I add my acid, it's going to attack and open up that ring, but it has to attack from the opposite side . Okay, And so that's how we get, finally, our diol. What's up?
For the halohydrin, will we not need to show the dashes and wedges on that?
Yeah, we should actually. It's true, because we do know that this is also an anti-addition. So yes, good call. All right, so throughout these 2 semesters, we're going to learn a lot of reactions that we can chain together to do these multi-step synthesis. So let's just make a note. This is our first time sort of seeing this here. All right, we can do this halohydrin formation. We put a bromine and an OH group. We treat that with sodium hydroxide. We form this ring. And then finally, if we treat that, we form this special ring. We call it an epoxide. And then we treat that with acid. We get a ring opening reaction to produce a diol. All right, and we can be, let's just be lazy and write and an enantiomer for each of these steps. Cool. All right, so we just got 8 more reactions to go here, and then, no, I'm kidding. We got 1 more, okay? 1 more diol formation reaction here, and the big difference is we're going to see a different sort of stereoselectivity, right? So instead of being an anti-addition for this diol, we're going to get a syn-addition diol formation reaction. All right, and this is not going to be a multi-stepper. This is going to be an all-in-one shot. Using osmium 8 oxide. All right, and you know, Sen asked a good question before, like, why osmium 8? I don't know, because it works, right? Somebody tossed it in there one time, they got themselves a syn diol, and we've been using it ever since. Why that particular transition metal? I don't really know. Could you also use, where's osmium? Ruthenium? Probably. I don't know, all right? Transition metals are weird. They catalyze reactions in sort of not so intuitive of ways, let's say. All right, so again, let's use a ring so we can illustrate our stereoselectivity here. The key player here is this osmium 8 oxide. We do this in everybody's favorite because it smells the greatest solvent, pyridine. Okay, and then in a second step, I don't even know what this would be called. Sodium bisulfite, something like that. Okay, everybody take a second and draw me my products here. We get a syn addition of these 2 OH groups. So what would that look like? All right, so we'll get a ring. Whoops. Our 6-membered ring. Again, it's a diol, so we're going to have 2 OH groups. Okay, but since this is a syn addition, they both need to be pointing on the same side. So if I draw one as a wedge, I'm going to draw the other one as a wedge as well. Okay, and I'm going to do plus this one down here where I do my dashes. Is that correct? I'll give you a hint. It's not, all right? So why? Why don't I have to include both that molecule and its enantiomer? Because it's a meso compound. It's its own enantiomer, right? I just drew the same structure twice. So if our product is a meso compound here, we don't draw the enantiomer as well. Just that one compound, right? That'll be my one product that I get. I get that stereo-specific product. I have to use my dashes or my wedges. You could have given me either or, but not both. Because we got to be able to recognize that there's only one product here because it is a meso compound.
And we can't put it as just a line because it could.
Say it again? You can't.
Because like the line has to be a wedge.
Oh, no. You could do both of them on dashes. So you could have given me just this structure or just this structure, just not both of them together.
Oh, I mean like just like a line of wedge, not like a wedge or dash.
Oh, no, yeah, you do have to include the wedge because you do not get the trans product, right? You can only use the straight lines if you get all possible stereoisomers.
Okay.
All right, cool. So that's it. Let's just kind of make note here regarding those 3 special things that we got to keep track of sometimes. This one here is a no mechanism reaction. Are we going to have any regiospecificity for this reaction? Why not? 2 OH, adding the same thing to both sides. You can't possibly have any regiospecificity. You're adding the same things to both sides. So no regiospecificity to worry about for this one. Okay. The one thing we do have to worry about for this one is our stereospecificity. This is another syn addition. All right, so we're going to just sort of do some review here at the end. But let me just say, we've kind of like taken a turn in the course here, and now we're very reaction focused, right? Up until now, it's kind of been about like building your tool chest of being able to talk about organic chemistry. What the heck does the hexagon with the second line even mean, right? That wasn't something that we knew coming into this course. So we kind of had to like lay some groundwork here. From here on out, this course looks pretty similar to this chapter over and over and over again. We learn a new functional group, we learn how to name that functional group, and then we learn a bunch of reactions that correspond to that functional group. The world of organic chemistry is broken down into those functional groups that we talked about because molecules that have similar functional groups all react the same. Right? We can put a double bond, an alkene, anywhere in a molecule, and we know how that molecule will react with one of these reagents. Right? So it's not really the number of carbons that's influencing things here, it's that double bond, that functional group. All right? And so that's very much so how this course is going to look. We kind of started off a little slow. We learned 2 reactions 2 weeks ago, 2 reactions last week, and then we got 6 this week, right? So these and we're just going to learn a few more next week, and a few more the week after that, et cetera, et cetera. It's a really good job, really good idea to start somewhere in your notebook, like a Grandmaster cheat sheet, or even better, to start building yourself a deck of flashcards to learn these reactions, right? Just to help keep everything straight. I remember when I was an organic chemistry student, I found this portion of the course really intimidating because I was like, I'm supposed to know how everything reacts with everything. Like, what the hell is going on here, right? And that's really not how it works. It's not like I'm plucking two random things and being like, go, tell me how this reacts. We learn a set of reactions, a set of reagents that correspond to a given functional group. And the best that you can do to keep these in little separate categories in your mind, the better it's going to be to not confuse everything, right? So that's why having this sort of cheat sheet list with an example reaction, and then do we need the mechanism? Do we need the regiospecificity? Do we need the stereospecificity? All those kind of in one place is really helpful. And so again, flashcards or like in the back of your notebook, starting a big master list, those are all really good ways to just kind of keep track of these various reactions that we're going to go over. Because again, all we're going to do is add to this list some more. All right? And look, I don't know what week we are in. What, like 10, 11, something like that? I don't know. Something like that. Anyways, we're kind of getting into the back half of the course where everybody's getting a little burnt out and it's like, oh my God, when is this thing going to be over? It's going to be over kind of before you know it. This happens. Courses have a way of both flying by and turtling by at the same time, all right? It's going to be over before you know it. You just want to sort of keep up. Don't let yourself check out for a week or two here, or it's going to be the kiss of death. We just got too much stuff that builds and builds and builds to kind of like check out and be able to keep up with everything, all right? So anyways, start thinking about how you're going to organize all these different reactions in your head and in your notes to help you keep track of what's what, all right? That's just a really good way to go about studying organic chemistry.
I have a question for the osmium. Since it's reacting to the photoxyl does it just like disappear somewhere? It's not hanging on us. It's just there.
Yeah, I mean, yeah, it's actually a. I want to say it's a full-blown catalyst. It doesn't actually even get consumed in the reaction at all. But yes, we have a bunch of other crap over here that just corresponds to the inorganic products of this reaction.
Okay, that's just like the end step that's going to be after this particular reaction.
All we care about, all we're really showing with our chemical equations in organic chemistry is what happens to these 6 carbons that we start out with. What happens to the organic molecule, right? We're always transforming our organic molecule from one thing to the next. And that's really what we're keeping track of. And we do so really specifically, right, even in terms of the stereochemistry. But yes, we don't really, I don't know what happens to the osmium or the sulfite or anything like that, right? And some reactions we do know because we have mechanisms for. Other reactions, they're just a black box. We just throw stuff into them and out comes the product. Okay. So in terms of studying chemical reactions, right? So first of all, we definitely have our homework system and that helps. That gives us problems, right? But you can just kind of make up problems on your own as well, because what functional group have we been talking about over and over with these reactions? So let's just, well, no, they're starting functional group, the alkenes. So let's just put down a random alkene. All right, and I got a deck of flashcards with all these different reagents on it. I'm just going to draw a random alkene and then draw a bunch of random reagents. And I should be able to tell you what happens in each of these cases. All right, so this is a great way. These are called reaction wheels, are a great way to summarize the reactions of a chapter. So this here, we're just going to take the same starting alkene, and we're going to do these 6 different reactions here. Cool. All right, so everybody take a minute and see if you can't fill in this reaction wheel here. All right, we'll double check with our neighbor, make sure we're on the right track. right, so let's do this first one here. Our chlorine. All right, this one's not too bad as long as you can remember the basics of our alkene reactions. This is an addition reaction. I'm going to get a chlorine on one carbon and a chlorine on the other carbon. All right, I'm going to be good and draw these spaced out. Okay. This reaction here, is there any stereospecificity to this? For the reaction as a whole, maybe not for this particular product, but for these halogenation reactions,
Yes.
right? These are what type of stereospecificity? So these would be anti-addition. So for those, I got to be careful and make sure that I don't need to have these dashes and wedges in my product, right? I have one new stereocenter, but is this a stereocenter as well? No, because I got these two methyl groups. So for one stereocenter, do I have to worry about dashes and wedges? No, only if there's two new ones that are created. So here I can get away with only doing my straight lines because I only have one stereocenter. This one is not. All right, and so this is going to save me kind of for all of these here. I'm not going to have to worry about it because this carbon has two identical groups on it. Okay, so we won't need dashes or wedges in any of our products. If we do HBr, again, we're going to get an addition reaction, but now I got to worry about where that Br goes. Okay, so let's just color these carbons on either side of our double bond, blue and red. Which one is the bromine going to go on? The red carbon, the more substituted, what we call a Markovnikov reaction. Okay, and real quick, I just want to make sure that this is clear. I put the bromine on this top carbon here. That would be the exact same as if I put it here. Would be the exact same as if I put it over here, right? So if you had any one of those, as long as it was on that red carbon, you're fine. All the same structure. All right, now let's do a slightly harder one. These ones, just looking at the reagent, it's pretty clear what you need to be putting on either side of your double bond, okay? Let's look at this one here, BH3 and THF and H2O2, NaOH. We got a lot of crap going on here, right? So what the heck am I supposed to be drawing as my product? So first of all, I've made the decision that I will give you a list of all of these reagents on the exam. That's not something you have to have memorized. BH3 and THF with H2O2 and whatever, NaOH. You don't have to have that list of things memorized, all right? What you do need to be able to do is to sight recognize them and say like, okay, this is the key here. The one for me that really pops out, because it's the name of the reaction, is this boron in this compound, right? This BH3. And so what's going to be my functional group in my product here? What am I creating with my borane in THF? This is an alcohol, so this is what we called hydration reactions, all right? But point being is, in my mind, I need to have alcohol and BH3 tied together, okay? There's nothing sort of obvious about that list of reagents that jumps out to me that I'm making an alcohol, so we need to kind of have these things linked in our brain here. All right, so yes, I'm going to be creating an alcohol. And am I going to be putting that OH group on the red carbon or the blue carbon? So this is actually the only one that we know about that is anti-Markovnikov. So this is a weird one where the OH group goes on the less substituted carbon. All right, my second reaction here, my sulfuric acid and water and heat. I mean, yeah, water might be a good key about what's going on, but we use water a lot. So, all right, again, we want to have this list of reagents here in our mind tied to that functional group that we're creating, an alcohol. Okay, and now for this one, we do want to put that OH group on the more substituted carbon. So it will go on that red carbon. All right, so let's look at this next one here. This one's also a little tricky. I have my Br2 and H2O. That's our halohydrin. But I got that in step 1. And then I have a second step where I add that NaOH. All right, so let's remember, we talked about this, our multi-step synthesis here. I'm doing not only this first step, but also this second step. So what should my product be? If I stop here at this second step, what's my product? That epoxide. So if I had just done the Br and OH, I would have that halohydrin, but now I did a second step with that hydroxide. So let me just show you real quick how we draw these. Okay, that epoxide. Let me draw my alkene, redraw my alkene real quick so we can just show. Right? Importantly, my epoxide will form with both my blue and my red carbon. Right? So if here's my original alkene, my epoxide that triangle is going to replace that alkene bond. All right, and then in the last one here, this osmium 8 oxide here. I want to have this tied in my mind to a diol reaction. I'm going to add 2 OH groups. Since I'm adding 2 of them, I don't really care regioselectivity wise. Just need to put 1 on one carbon and 1 on the other carbon. Okay, so if we just draw a random alkene, we should be able to pick any one of those reagents that we studied in this chapter and say, all right, well, what product is being formed, right? So again, a flashcard activity where you got your reagents on flashcards, you draw a random alkene, pick a random flashcard and draw your product. That's a great way to study. All right, let's do one more here. Okay, so we got two more reactions that we're going to do here. So I have my alkene here. Let's do this Cl and H2O first. This is those halohydrogen reactions. All right, I got a red carbon and a blue carbon here. My red carbon is more substituted, so what am I going to put on my more substituted carbon? The halogen or the OH? The OH. The halogen is going to go on the less substituted carbon. Okay, So now let's look. We have this reaction has stereospecificity. And I've created how many new stereocenters here in my product? Here's one, and here's one. So what does that mean? Do we have to do dashes and wedges or no? Yes. All right, cool. So what we have to remember about these reactions is that they go through that cyclic intermediate, just like with our other halogens. So they're going to be an anti-addition. So I'm going to add one of these groups onto a wedge. That means that the other one, I got to put on a dashed bond. Okay? And remember, I'm not going to touch my zigzag here. I'm going to let that stay as these straight lines. Only the things pointing up or down I'm going to change. And since I put a since I put a dashed bond on that OH group, I have to switch my methyl group to being a wedged bond. All right, and remember then we first asked ourselves how many of those stereocenters were formed. We got 2, so we had to do the dashes and wedges. And then we're going to ask ourselves, is this a meso compound? Is it a meso compound? It is absolutely not even close to being a meso compound. So we need to also include it's an enantiomer. My wedged bond needs to become dashed bonds, and my dashed bond needs to become a wedged bond. Okay, similar down here. All right, in this case, we don't even have to worry about any regiospecificity, because we're adding the same thing to both carbons. So I'm going to put an OH group on one carbon, an OH group on the other carbon, and I'm going to ask, how many stereocenters do I have? In this case, I formed 2 new stereocenters, so I'm going to have to worry about the stereochemistry of my product. My previous example was an anti-addition. These are syn additions. So if I make one of those OH groups into a wedged bond, I'm going to do the same thing for the other one. All right, and again, I don't want to touch that zigzag backbone. I'm just going to change what's sticking off. If I put that OH group on a wedged bond, that means my methyl group has to be on a dash. This one's a little closer, but still is not a meso compound. So I'm going to also include it's an enantiomer. Boom. All right. So again, the stereochemistry is definitely the hardest part of these reactions. There are a few reactions, not all reactions, we've made notes of which ones they are, that are either syn or anti-addition. When do we really have to be concerned about that? When we have an example, or when we have a product, like in this example here, where we have created 2 new stereocenters. That lets us know we're going to have to draw our specific stereo products here. Well, both of these molecules have 4 total stereoisomers. In our reaction, we only produce 2. We only produce a subset, so we got to draw those 2 using those dashes and wedge bonds. Cool. All right, that does it for